Hello, good morning and welcome everyone. I'll just give it a minute before we actually start so you can get accommodated to the platform. Today, I'm going to be the moderator and replacement of Ivan from Lux Innovation. My name is Thomas and I organized this webinar in the background here in service of our project of the Luxembourg Digital Innovation Hub. And personally, I am from the University of Luxembourg and working for the Competence Center of the university. We are partners in the Luxembourg Digital Innovation Hub and we focus on skills and training. So this is also how I would like to start the presentation of our L-DIH today from the side of education and training. If you have questions, don't hesitate to ask them in the question tab. If you need to discuss something, use the discussion tab. The speaker will later, or myself, we will later respond to it at a given time or even asynchronously in chat if you want. What you see on this slide here is the structure of our Luxembourg Digital Innovation Hub. So many might ask, what are you actually doing? We are supposed to deliver certain services to companies free of charge, but not free, meaning that we are funded by the European Union and the Luxembourg Ministry of Economy to not be dependent on service contracts with companies. So when we offer our services, we actually do it for the betterment of yourself and of your company. And we are divided in four sections here. One is the test before invest, or the technology testing, which is traditionally taken by LIST, Luxembourg Institute of Science and Technology. There is the support to find investment and everything that comes with it, which is taken by our consortium leader here, Lux Innovation. On the lower right side, you find the innovation ecosystem and networking. This is where the full DMA and the light DMA are located. Those are digital maturity assessments provided by the University of Luxembourg, not by us, but by the Faculty of Sciences and Technology here of our university. But there are also other services there, like the cybersecurity assessment from the House of Cybersecurity. So this is very manifold here, the offer in that section. Then finally, on the upper right, you find skills and training. And here we offer four distinct services. One is a digital skills maturity assessment that we can conduct with your company and your employees, where we can find out the competences that are required for the next innovation, or we can just ask employees what they believe they might need to train in order to bring the company forward. So this survey is very adaptable and it can be adapted to your needs. We offer guidance and training roadmap support here for companies for specific training needs. And we do that in partnership with organizations in Luxembourg, like the Luxembourg House of Training or other training providers. So we are totally agnostic here and can also help you to get in contact with trainers and consultants to adapt their trainings or the training packages to the needs of your company. For that, we organize workshops. Workshops are opportunities for trainers and consultants to adapt their offer or to get together with representatives of companies to do so, or to start an internal training and competence program by facilitated through us, but something like a knowledge transfer within your company. And finally, the awareness sessions that we all share as a service here, of which also belongs the webinar. Please take a look at our training catalogs. This is where we list all the different training providers with which we work together with, and trainings that already exist in languages from German, English, French, and Luxembourgish, and even Portuguese. So this is a little slide on our training offer. I don't want to go deeper into there, but if you're interested in the training offer, then please follow one of the QR codes or ask me in the discussion later on. Thank you. And without further ado, I want to pass on to Alexander Shukobotsky, who will tell you something about green tech and saving money with AI-assisted load distribution of electrical systems. Alexander is a renewable energy modeler for a company called Advanced Infrastructure. There is a QR code here, a link, and he can surely tell you more about that. So Alexander, the floor is yours.
Hello there. It's nice to talk with you and provide this webinar. So I will start by discussing low carbon communities in terms of possible employments, deployments, possible scenarios, and how that can be done, like on national level, how it can be scaled up, what the prerequisites, and all the other details which relates to low carbon communities and potential challenges in their deployment. And this will be considered both from carbon perspective, like reduction of emissions, as well as a monetary perspective as well. So if I go like to some overview, so like everyone wants to reduce stress on the grid, and it's kind of like of the high priority everywhere. And then how like the more renewable energy is integrated to the electricity grid, the harder it is to predict the outcome of the areas. So previously, like in many locations, like if you want to know if any kind of power station or secondary substation, well, it was known like what is expected load in the area. But let's say we don't know that because we now integrate like renewable energy. We get like a lot of new information from various of like low carbon technologies, and that affects the demand. And that can cause like trouble nationwide and grid-wise because it's impossible to know where you can connect low carbon technologies or when you should connect them, or like is it actually feasible to connect them? Is there enough capacity?
Alexander, sorry, 1 second. It seems like many people are waiting for their registration confirmation. Marta, can you check if you have let everybody in who asked for a registration? Sorry, Alexander, you can continue. Sorry.
Okay, so let me continue. So for example, like let's consider the case of the UK, but it's the picture is typical for whole Europe. So on the high voltage levels, like if we turn on the picture, like on the right, the top green one, there will be like grid supply points which supply large areas, and they're connected to the substation, they distribute the energy, and they're quite big, they're visible, they're monitored. If we just go down to bulk supply points, they have slightly lower voltage. They're also visible, they're also monitored. And then we go down the line, you get primary substations, they're also typically monitored, and they're also visible. We know like their consumption. But when we go to secondary substations, which are typically connected to like residential dwellings, and that's which will be connected to energy communities, they're typically unmonitored. There are some which are monitored, but not all of them have this information. And in some cases, it's impossible to get any results. It's not of benefit to install any metering for the secondary substation because it's too expensive. So other solutions are used. For example, in the UK, there was a program to allow like information about smart meters to be released anonymously. Smart meters which belong to monitor energy for electricity consumption and belong to each residential dwelling, release it in an anonymous way across multiple customers. Sorry, not customers, but across like small areas like secondary substation areas, which were they aggregated. so that they can provide some information, insight about these areas, but not all areas have this information. And that's kind of needed to be extrapolated. And that's important to just know the location of where the energy community can be present. Because as I said initially, before even putting somewhere energy community, we need to know if it's possible to put these technologies or low carbon technology like heat pumps, battery storage, PV panel or solar panels, or like any kind of like other energy storage devices into the dwelling. So unfortunately, like on the lower scale, where we actually need to put them, we have very low visibility. And that was tackled by some project which was led by AETL. It's called Digital Twin Energy Grid and Trustworthy Mail project. So one was just a project which is running to collect information about smart meters, and another one is to deploy the model to get the areas, information about areas and about parameters and loads and all the information which will allow the deployment. And these projects are kind of vital and able to provide more communities. For example, on the Red Wolf project, there was a nice idea. It was investigating houses, dwellings, residential with multiple LCT technologies. It had battery storage, it had storage heaters, it had heat pumps, it had many other technologies, but without information about grid, it's not clear where it should be put and what actually are effects of these technologies. So if I move slightly to the next slide, there'll be a bit more detailed approach and like about the load forecasting. So here, like for example, there are a model produced in one of the project, which was Trustworthy Machine Learning project, and in here, if you can see on the left image, there are multiple small areas. Each of this area is associated with a secondary substation, which are typically connected to residential dwellings. And by forecasting the load in this substation, it is possible to know the consumption pattern in the area. This will allow planners, or local authorities, or like DNOs, to either say yes or no to installation of LCT technologies. That because they will know approximate load, approximate behavior of the system, and they can easily see yes or no. So knowing this information is kind of critical to determining where the energy community can be placed and where like LCT technologies could be formed and how the energy communities should be defined. Yes, there could be many definitions of energy communities. You could consider energy communities as a few buildings or dwellings sharing the energy between each other, or it could be just joint sets of union of buildings which are in close proximity to some substation, which work together to achieve the same goal and work in a predictable manner for the DSO or the DNO. So, for example, on the right side of the image, there is some plot. This is a plot for some model demand, which is resolved half-hourly for some area in the UK. It's just kind of the code, and it's visual, and so we know like approximately demand in every half hour and what it could be, depending on demands from the known areas. So we also need to know some other areas to implement this technology. Let's go a bit further. So what was the scope for the Red Wolf project? So the Red Wolf project, which ran from 2019 to 2023, was assessing two global challenges. So they can be like simplified in two terms. So the rise in energy cost and climate emergencies. So the Red Wolf project tried to tackle both at the same time. So and how it was done. So the Red Wolf project piloted about 90 buildings with different LCT technologies, which are smart controlled, and they are all controlled all together and connected to external signals. So one of the signal was available straight away. For example, carbon intensity was live available for the API as well as its forecast. So you're able to tune the model, or like tune the equipment inside the house to follow the signal, and which will result in carbon savings, which were quite big in this case, about 58 or 62%. And also, in the same manner, there are like places where there are dynamic tariffs. So that relates to rising energy costs. So dynamic tariff is a tariff when the energy fluctuates every half hourly, every 5 minutes, every 2 minutes. So the energy price is not fixed; it's variable. So and sometimes it's predictable, and if it's predictable, it will be known like usually like 1 day in advance, 2 days in advance. But sometimes it's completely dynamic, and it's related to external factors. For example, in some areas, the dynamic tariffs could be connected to the speed of the wind turbine, and depending on the speed of the wind or other like atmospheric parameters, the energy price will fluctuate. And this was taken in account in the Red Wolf project, and allowing it to save also the monetary part by following the available signals, so like weather parameters, to drop down the price of the annual bill for residential dwellings. And like on the bottom panel, you can also see like out of the box picture, which shows how the green Earth can transform to the Venus if we get too many CO2 emissions or like any other like greenhouse gases that will trap the energy inside the planet and make it really, really hot. And we don't want to do this, so we introduce various systems to mitigate it and various low carbon technology. So I will go for the next slide and just discuss briefly how Red WoLF actually like worked, what were like the main principles behind like the savings and how it was achieved. So it was using the typical mechanism, which is known as peak shifting. So if we know when the peak of subsignal is arrived or when the peak of consumption is, we'll try to avoid this peak and just move the energy intake from the grid from for the better period. And for this specific case, there was a special uh, optimization mechanism designed for the hybrid energy storage systems, which consisted of heating elements, battery storage, PV generation, and heat storage, domestic hot water storage, and the battery storage. And this technology was designed, called by some uh, double threshold algorithm, which we called it in the Red Wolf project. However, the main part, what it does, it just shifts the demand to periods where either carbon intensity is cheap, or the price is cheap. That will preserve. That will this will enable us to save the money or reduce the CO2 intake. And also, it followed the second target, which should be always fulfilled, is like energy needs for the dwelling. So it was also adaptive. So the algorithm would recalculate what it needs to done every minute or so. Fortunately, the methodology we made is what it was lightweight. It could be even deployed like on edge systems, on smart devices which are plugged in home. So it's very quick, it's very fast, and quite reliable because it calculates every minute. So it always knows how much energy house needs, and it gets some forecast from the previous consumption, but it also like gets information about current consumption levels and what is expected, and what like temperature was set by the user and so on. And these were published in some peer review papers as well as like a novel mechanism of controlling the systems. And if you look like on the right image, there is some design of the tools, so and how things are interconnected. For example, green lines will show the preferable energy distribution. So as we can see, the preference is always to renewable generation. But the yellow lines show like the second preference. So for example, if the energy is taken from the solar panel, and if it needs to be used by appliances, it will be taken from the battery if we don't have enough energy from the sun. However, if we want to get like more energy, we will take it from the grid, but it's like a worst case scenario. We don't want to do that. And why the battery is yellow? Like why not thermal storage is yellow? Like why not domestic hot water is considered yellow, but it is considered green? Is because the battery loses its power, where like thermal storage, although loses its power, all the energy is transformed to useful heat energy, which will be used later within the dwelling. And if you want to have like more details, you can look in the papers, which has links here, and we'll describe like the left methodology behind the optimization approach, and that will just show how that actually was worked and what's a like baseline equation behind that project and behind the system control. So this all was integrated in 90 houses across multiple countries in the EU. And that system was mostly behind the meter. So the user can only like set up like some information about like what heat level he wants on the thermostat. That's it. But there was no other control parts from the user side, as it was always behind the wall. So there was quite a few less interaction with the user, which will be generalized, who should be generalized in the future. So the user should have some more control and more visibility of what's going on, because for user the only thing it was he was he was able to see would be like reduction of the bill. That's it. Like maybe it's the only part which is relevant. We don't know. Like, but that's what the only visible information for the user. And both targets were quite successfully achieved, as it will be shown and the next slide. So there are some photos on the right side. There are some information from like visualization which we had like internally for the consumption. There are some images of the paper on the right side of the slide. So in the ballpark, like there were 90 fully equipped houses with batteries, hybrid energy storage system across Northwest Europe. So that includes Ireland, the UK, North France, and Luxembourg. And the system was slightly different in Luxembourg and France. For example, and in the UK. In the UK, like the preference was to the storage heaters technologies. So storage heating technologies are quite cheap. And that was also part of consideration of the project. The project supposed to be cheap. Storage heaters at that time were much cheaper than heat pumps installations. And that was a choice. However, like in Luxembourg, the heat pumps were used directly and was shown like possibilities to be controlled by the same type of algorithm. There is no big difference between the storage heaters and heat pumps in terms of control, but there is a difference in terms of energy consumption. However, like we found out during our research on the project that even if storage heaters consumes 3-4 times more energy, just due to price fluctuation in the time of use tariffs, there'll be no difference in the bill reduction. Even if you use less with heat pumps, the price will be essentially the same as if you use cheap storage heaters. And that was interesting finding, but that doesn't really help to reduce stress on the grid. So heat pumps are going to be always like the preferable solution because they use less energy, and that will help like balancing an operation of the grid in total. And some other outcomes of the Red Wolf project was quite surprising. There are 7 peer-reviewed publications published, which, because the project was quite experimental and there were quite a few things to be done. And one of the big advantages was designing like a fast pace algorithm which adapts on the go, and it's allowed to save the emissions by 58% and reduce the price by 62% for an average for residential dwellings. So that's kind of like a good achievement. But this project didn't have any take on consideration of the grid of whatsoever. It was focused only on residential dwellings as a singular unit. So what is the challenges? So there are a few major challenges for the system like Red WoLF. And one is scalability. Like as I showed you initially, it is not possible to install the LCT technologies everywhere we want to, because that can overload the grid, and the grid is not ready for that. So we would need to upgrade the grid within some time, yes, but we also will need to identify suitable deployment areas. Without, for example, identification of suitable deployment areas, it will be hard to promote energy communities. For example, if you have one house, you can locate a house or two like in the areas, but in some areas you cannot have more than 3 or 4 houses using LCT technologies without disturbing the grid. And that is a challenge. So that areas could be located and they can be informed to local authorities or to DSOs or DNOs or other grid operators, depending on how the structure is functioning. And potentially the transformers will need to be reinforced in the areas to accommodate new technologies and allowing low carbon communities. The other thing which can be used, like, for example, these areas can be found by using tools like local energy planning tools, which do everything interactively. For example, the company I work for designed such tools. But there are like others as well which do similar. They design tools which show which areas, which buildings are suitable, which areas have what kind of capacity, and so on. So these kind of platforms can be integrated to decide where the local low carbon community can be placed. And it's very crucial because otherwise, once again, the grid will be in bad shape, the transformer can be buried, and so on. The other aspect is we will need to have some user education and engagement. In the Red WoLF project, for example, we didn't have this aspect, and we found out that in some cases, without the education and engagement, the dwellers will just turn off the equipment and they wouldn't benefit from the system at all. They see a lot of buttons. They see hundreds of buttons. They see like 10 buttons. They see 20 buttons. They just want to press it. And without education, it will be hard to control. So one solution is to get all technologies with one potential, I don't know, like a tool or visualization equipment, which will show what's going on and have some control panels, but it cannot be, I would say, hard turned off unless it's just turned off from the plug, or similarly like a back switch. Just not having equipment with multiple buttons can cause some troubles. The other thing is to formate the energy communities. That can be both challenging from the practical application as well as like legal aspects. For example, in some countries, there is no clear legislations on the matter on how to form the energy communities. So yes, you have like multiple houses with different carbon technologies, but how they will interact with each other, that's unknown. Like, for example, there are no regulations. For example, in some places, you cannot share the energy between the houses. So they somehow will need to communicate virtually. or by other means. Or for example, let's say you have like 5 houses. You live in your nice energy community. You have 5 houses, or 6 houses. You all live happily, then one of your neighbors sells a house, and that's it. You just can say no to energy community, and then all the strategy work together can be ruined because of it if you like hardwire everything together. So there will need to be some balance. And the final aspect to for location of energy communities is the abundance of dynamic tariffs. Okay, like for example, for scalability case, like it's okay to say like we will reduce the CO2 and reduce the emissions, but how the users will look at it, like they don't see any benefit of it. Well, unless they're like really into like ecology, and then they want to spend tens of thousands of euros for low carbon technologies, and they're happy to buy it, but they will buy it anyway. But how to make some incentive for other users, which are not part of these low carbon communities? So one aspect is to show that, for example, in the presence of dynamic tariffs, which varies every like 5, 10, 20, 30 minutes, can have negative price in some moments, and with high fluctuation rates, like for example on it could be seen like I don't know, like a stock exchange market in some cases. So it's very volatile. So you would need to like have some dynamic control tool which can interact with it and get the most benefit for you as a user. And if it shows that it saves quite a lot of bill on your side, you will be happy to go. So on top of the savings by using like low carbon technology by itself, you can connect them to some smart tariffs which help you to penetrate technology even further down. And these tariffs are quite crucial to the digitalization. However, they also have like a bad effect on the grid predictability, because the price does not necessarily relate to the standard use of the energy patterns within like the area, and that could be seen like in the project, like in the I was showing you previously. There were like some areas with really abnormal consumption patterns because most of the residents in this area were connected to some dynamic tariff, which was connected to the speed of wind turbine. And the speed of wind turbine, it depends on the wind speed. So if you don't know the wind speed in the moment, you don't know the price. I mean, you can predict the wind speed, but if every single part is like that, that makes a nightmare for the grid operators to predict it without using some sophisticated model, and they take quite significant effort to do research on it. And once all is done, yes, we can scale the energy communities, but we will need quite a lot of components to do so. So what can be proposed like in high level architecture? So there is this little diagram on the right side. So let's say we have some tool which is Plus, for example. It's local energy planner tool. Plus means it's interactive, it's digital, it's online, and it's can be connected to digital twins or other means. This will allow you to find the areas suitable for LCT deployment. So you can see like which areas are suitable, which buildings are suitable. So for example, it can tell you like if the roofs needs reinforcements, if you need to spend that much money for technology in this building and that much money on the building adjacent to it, like what kind of technologies can be installed, what the size of heat pump is needed for this building, what the insulation level of the building, and all this information can be meshed together and linked. It really helps like planners to decide which buildings are suitable or not suitable for technology, as well as DNOs to see what level of consumption these buildings will have. For example, if they switch from gas or oil use to electrical use. And once we know which buildings are suitable, we just deploy some LCT technologies, which can be later smart controlled. However, once we introduce a smart control system operation, the patterns in the areas will deviate. So that will need to be fed up back to the local energy planning tool. So it will be like kind of cyclic process. So once you deploy some tools in the area, you first will need to deploy them. You will have some predicted effect, but then you will see like real effect. And then you reiterate this process again and again until you can get like more and more smart communities. And that is kind of crucial. So for the development of low carbon technologies in the area and assigning like low carbon communities, which can benefit of working together. And one of the aspects why low carbon communities are beneficial is when the installation happens on LCT deployment, it is always cheaper, like in most cases, it will be cheaper to install these technologies in the area rather than installing it dwelling by dwelling. And that can help incentivize more users to have a go with a bit of low carbon technologies, and then that can be connected to smart control system operations. And at the end, this result, they will see the reduction of their annual bill, and potentially, if they have like smart devices inside the visualization tools, they will also see how much carbon was saved by them and like how much less their houses are emitting now in comparison to what they were doing previously. But there are all other aspects for energy communities which can be used apart from price decrease for the users. There are also other goals like these communities, because it's not more like one single dwelling, they can be used as shared storage assets, which can coordinate local balancing in some cases and engage more actively with the grid. So the larger is the community, the bigger player it becomes. So they might have more. They can provide some service for the grid. For example, they can use. They can be thought as aggregator if they have enough storage technologies, or they can provide other flexibility service for local optimization. So let's say we have like a few low carbon communities, but then in proximity of like, let's say like smaller region of secondary substation. However, they are so close to each other and they communicate with other secondary substations. So they in the end they can affect the primary substations, and you can go like up to the grid diagram to the higher level of powers, which is distributed. So all in all, like if it's all connected, all visible, and they can all interact with each other, they can like preserve the grid for a longer period. And like how can we also get there, like from a technical perspective? Let's say like we have like all we need, we have identified the deployment area, we have scalable system designed. We still need to uh, activate the users and educate them. But in this case, I just propose some tool which use user interface, which show some visualization and like explain the user how the interaction can it be, and with the help of like modern AI tools, it can even explain them, it can dictate them words. Oh, like there are multiple options like this case. That can trigger behavioral change in like education levels, so as well, which can benefit energy communities, but that's not necessary. Like behavioral change is not fully necessary if you have a smart system inside the house. Then you can then the energy community can be formed, like you start like a few dwellings, then they interact with each other. The app says like there are like dwellings nearby, and you just connect them with each other like with other app. You can have like tariff and grid integration. So even if you don't have dynamic tariffs in the area, sometimes like big energy providers or like industries, they do have dynamic tariffs regardless if it's not feasible for residential, and that can be negotiated and further down, smoothing down the policies. So that's how you can go there, like in simple terms. But if you want to look at more technical design, like of how these dwellings can interconnect, you can see like on the image on the right. So there is a both-way connection between DNO and the server, which is displayed like as some electric with electricity symbols here, and it's connected to the cloud or the server. Doesn't matter if it's cloud computing or the local computer. Like the more modern approach is a preferential way to put it like a local servers because they're cheaper to run than the cloud servers in the current day. And that can provide some services to DNO, so like at least produce some information which they can see easily. They can export active and reactive power. They can do load shifting for storage or switching off the device. But the server needs to some other outputs. It needs to some renewable generation forecast. So if you had solar panels, it will need to have PV forecast, but it also needs demand forecast. It might need to have CO2 forecast. It must have some dynamic tariff forecast to follow the price. And it also needs to know some information about other users which are in energy community, like what are their forecasted used to do in case the building is involved in some balancing or peak shift in a large area or large some schemas. And then this server passes information to the controller hub, and then it interacts with devices, which is like batteries or like electric cars. It can be charging idle. It can be like storage heaters. It can be heat pumps connected to water storage. It can be many type of possible devices. And then that is also one of the important bits. Like this information should be displayed for the users, so users know what's going on. They know how they interact. This tool will provide some visualization of total saving and the demand management. And all in all, like if you follow like a few steps like that, like you have like a good system design for the dwelling, you know where you can place the energy community, and you know that the grid will be in favor. You have some financial incentive or carbon incentive. This local low carbon community can be formed. And I think that's it from my side for today. Thank you for listening. And I'm happy to hear any questions.
Thank you for the presentation. I have a question received from somebody who couldn't log in after registration, and the person is interested in knowing how this how energies, communities, like you described them, um, can you imagine any benefit for small companies? Uh, because you talked about residential housing, and that was the focus of the Red Wolf. But can you imagine any benefits for small companies?
Oh, of course, yep. Yeah, that's yeah. The small companies can be treated the same way as residential dwelling, like they just will have different regulations and how they're formed. And it might be the case that it will be much easier for small companies to form the energy communities rather than residential dwellings due to GDPR issues. I wouldn't say it's issues, but legally speaking, it's much harder to form energy communities with a singular dwellers or like a private person rather than the company because uh, they can be easily done with documentation. They can agree on some part, and here we go from there. But if it's like a private user, it's much harder to do so. The same pattern can be used, just different technologies will be implemented, or similar technologies will be implemented. The tool I was talking about, it initially it has like both. It has separation between domestic and non-domestic technology. So if we go for non-domestic, it will be industrial-led technologies, and it will work for industry as well. So that will be the similar situation, just maybe education will be on the earlier side. So because legal education is important in this method. You don't want other company to be suffering because you did something wrong, and then it will be a legal nightmare.
Yes, obviously. Okay. I don't see any further questions. Or
Hello?
hello, can you hear me?
Hello? Yes, yes, yes.
Sorry, I don't see any further questions. So maybe just for reference, can you put the name and the link to your company again, where people can reach you in case they have questions?
Okay, so I think the reference was on your page.
Yes, it was on my page. I can go there if you want. Sorry. And do you operate outside of the UK at the moment with this company?
For now, like let me just tell for now we mostly focus on the UK. We had some pilot sites in Spain, in Ireland, but it depends. The main issue is like we need quite a lot of data to make a product. We need the planning data, we need the infrastructure, we need cables, we need all this kind of information. And if we want to onboard a new country or new area, we need to get first this information. It takes time, but we are expanding. So
And what about the transferability? Isn't it very similar across Europe, or would you
uh,
say absolutely not?
it depends. All this information is different. I would say there are. So if we talk about like cables information in some countries, it's more easily available and some not. Smart meter data can be more easily available in Europe than in the UK, but some countries they don't even have it. So it's hard. It depends on country by country basis. So that needs to be evaluated before like these kind of technologies go to the country. And it takes time to prepare and sort the data. What we found in the company that most of these data and information is disjoined in multiple government organizations and they never match together at all. So onboarding a
Okay.
new place, it's possible. It takes time, and it's what we're doing. We're onboarding more and more places every half year, or 3 months, and we try to
But
make it as more as possible. But it takes time. We cannot onboard like in one go.
a
It's
commitment,
a
yeah.
process. It's a long process. It's not an easy process. It's a big process, big data, and big results. I guess it really helps people to know where the technologies can go. Like usually prior, the people will just bump down the technologies anywhere, and then the transformer will go off, and then the DNO will come and fix it or put the stronger voltage transformer. But now they save a lot of money. For the UK, the estimate was I think billions or something. So it's very worth to use it, but not many countries do it now.
Okay. Then I hope with the second Red Wolves that's about to start, you will get much more opportunity to explore this further, to get more data as well.
Yes, hopefully, hopefully.
There are there have been no more questions in the meantime, so I would say we end the session here. And
Okay, then.
yes,
Okay, then.
thank you
Thank you
for
for
joining
listening.
us.
Thank you for listening. Have a great day.
Yes, you too. See you soon.
Okay, then. Bye.
Bye bye.